Hello, everyone. Thanks to come to this technical speech about thermoplastic flexible hoses with a special focus on CO2 applications. My name is Paolo Guasti. I work at ZEC. We manufacture thermoplastic flexible hoses for several applications ranging from oil and gas, hydraulics, painting, and of course, for refrigeration. So let's start. I will talk about, first of all, about the construction of flexible hoses. Then I will spend a few words about the standards that cover the use of this product on refrigeration systems. And we will see that these standards, written some years ago, do not take into account natural refrigerants nor CO2. So we will see how the requirements of the standard do not take account natural refrigerant and how ZEC decided to improve these standards with a series of our own tests in order to give to the market a really reliable product for CO2. So this is the construction of a thermoplastic flexible hose. This one is our hose for CO2, but the construction is in general the same for every thermoplastic hoses. There is an inner layer made of polyamide with a barrier layer inside. The key features of the inner layer is the compatibility with the gas. And also another important key features is the permeability, but we will talk later about permeability. Then this is a reinforcement. The reinforcement could be with wires, with braid or spiral, or with textiles. In our case, we are using high tensile brass plate steel braid for CO2. And then the key features of the reinforcement is withstand the pressure. For example, the 120 bar sometimes used in CO2. And then there's the outer cover made in polyamide. The only features of the cover is protecting the underlying layer from the environment. So these one are the standards. The main standards for use of thermoplastic hoses is the EN 1736. Also, the EN 378 cite the EN 1736. This means that if you are a manufacturer of a refrigeration system that must comply with EN 378, you must install on the machine only product that comply with EN 1736. It was for the first time developed in 2000, but it has a main review in 2008, where to the requirements has been added also the impulse test and the helium permeability. So this is the list of the main requirements requested by the standard, the EN 1736, for flexible hoses. There is a fatigue test where the hose is installed in an impulse test bench and must withstand 250,000 cycles at the service pressure and the working temperature. This test is made with oil. Why oil? Because it's much more easy to manufacture an impulse test bench that use oil due to compressibility. But the key point is that when there is a leakage, you are not able to find a leakage. Not every time you find a leakage when we are using oil. So we decided, and we will see at the end of the presentation, how we changed these requirements to be more according to CO2. Then there is the burst test. The hose must withstand 3 times the service pressure. We decided to increase this safety ratio from 1 to 3 to 1 to 5 in order to give more safety to the product. Then there is a vacuum resistance, quite easy, and the permeability. The permeability is a key feature of plastic. It's not like soldering, welding, when copper do not have any permeation, and if the welding is properly done, there is no leakage. Plastic always have leakages. So the standards require 3 main classings. The class number 1 is the one with the lower permeability. And the standard request to test the hose in 2 conditions, 32 degree and at the saturated vapor pressure, and 100 degree and the maximum surface pressure. So take a look on how the permeability is measured, because it's a key feature for this product. It's the so-called integral test performed with helium, so widely used in refrigeration, also for heat exchangers, with an interesting addition to keep the product warm during the test. Because the permeability of plastics strongly depends on the temperature. But the standards require to disconnect the heat source after you achieve the temperature, disconnect the heat source, and then create the vacuum. The vacuum helps to keep the temperature, to keep the product warm. But the standard do not require the control of the temperature during the 1 hour test. So we decided to make a slight modification of this test, and instead of using, for example, warm air, we decided to put inside our machines 4 air lamps in order to keep the product warm along the 1 hour test. And then when you have the leakage measured with a mass spectrometer, you have to convert it, because no one are interested in millibar liter per second, that it is the unit measure that the mass spectrometers give to us. We are interested in grams per year. So the standard provides this very useful table and with this table we can convert from helium leakage to refrigerant leakage. But if you take a look, there is no natural refrigerant and no CO2. So how to handle natural refrigerant? The standard do not take account of CO2. This is our permeability test that we have in our company, in our laboratory, able to perform tests at 120 bar and a maximum temperature of 120 degrees, with the UR lamps to keep the product warm during the test. So, but what about new refrigerants? How to convert a leakage coming from this mass spectrometer to a real leakage in grams per meter? And also, what about CO2? Because if you remember, the standard requires to measure the permeability at 32 degrees and saturated vapor pressure. But the CO2 do not have any saturated vapor pressure at 32 degrees. So how to handle? Take a look. First of all, how to convert the leakage coming from the mass spectrometer to a real leakage expressed in grams per year. Because I'm a physicist, I'm not satisfied if I do not put some formulas in any presentation I did. So you are forced to check some formulas. Let's say that because in plastic the phenomenon is called effusion or permeability, the permeability can be approximated with a molecular flow. In molecular flow, the Gram's law can be applied. The Gram's law comes from the kinetic theory of gases. I don't want to spend time on kinetic theory of gases, but what they say, if you're performing a leakage test with the same product, the same pressure and same temperature, the ratio, and A and B are two gases, the ratio of flow of the two gases inversely proportional to the square root of the molar mass of the gases. That is quite obvious. Smaller is the gas, greater is the permeation. But it is true in this case, in the Gram's law, the flow is in number of molecules per unit of time. And we do not care about the number of molecules. We care about grams per year. So we can we apply this formula, and we find out that if we express the flow in grams per year, the formula is inverted. This means that greater is the molecular mass of the gas and greater is the leakage. Because it is still true that the number of molecules per unit of time is higher if the gas is smaller. But a smaller molecules also has a lower molecular mass. And so, this one is the end-run test. It's a new requirement for this product. The standard do not take care about end-run tests, but when we start to develop hoses for CO2, we think about how we can to be sure to give to the markets a really reliable product. And so what is the weak point of the plastic? The plastic changes its features when you warm the plastic and when you cold the plastics, because the mechanical feature of the plastic changes as a function of the temperature. So the key point is try to simulate the real market condition. So what we did, we take our product, put inside a climate chamber, plug at both sides, and change the temperature and the pressure with cyclic variation. In this way, we are able to simulate the real condition of a flexible hose, for example, attached to a CO2 compressor. And we reached more than 2,000 cycles. That's a really good result. Also, we perform what we call an overheating test. Also, the overheating test is not required by the standards, but this test, we exposed our product to a temperature that is over the maximum temperature we declare on our technical data sheet. And the reason is that we want to be sure that if the hose is exposed due to a malfunction, for example, to a higher temperature, there is no burst. So there will be a leakage, but there is no burst, so the product is still safe. And so take a look to this conclusion table. On the left, we have the requirements of the EN 7036. There is the impulse test. We decided to make some modification and add to the impulse test, because the impulse test is made with oil, adding at the end of the test a nitrogen test performed at 2 times the working pressure, just to be sure that after the impulse test, the hose still can withstand the pressure with gases. Then, as I previously said, the burst pressure from 3 times safety ratio goes from 5 times the safety ratio. The permeability is said to be measured at 32 degrees in saturation pressure, because CO2 do not have any saturation pressure at 32 degrees. We decided to slightly change the condition in such a way to test our product in the worst condition. And then the standard do not require any temperature control during the helium test. We decided to put an additional temperature control during the helium test, and also at the endurance test, as I talked before, and the overheating. And all these tests, just to be sure to send to the market a really reliable product for CO2. I'm done. If you have some question, you will find us at the building number 7 and the booth 149. I'm done. Thank you very much.